Gears inside a rear axle decide whether a car glides or grinds. For most of the 20th century, nearly all of those gears could be traced to one factory in Rochester, New York. The company behind it began with an Irish immigrant who fled famine with nothing and was later saved by his daughter, who entered the business at 11 after typhoid killed her brother. She became so well known that Henry Ford thought she had invented the firm's greatest machine herself. Then her own family pushed her out. This is the story of the Gleason Works. William Gleason was born in 1836 in County Tipperary, Ireland. In 1851, at 15, he crossed the Atlantic with his mother and brother and settled in Rochester, New York. Rochester was then a rising industrial city on the Erie Canal, with flour mills, river traffic, and water power from high falls. For a boy with no money, no connections, and no formal engineering education, it was the right place to learn metalworking. He apprenticed in machine shops, then worked at Colt's Armory in Hartford during the Civil War, where he saw interchangeable manufacture at scale. That experience mattered. Back in Rochester, he opened his own shop in 1865 and spent years making the ordinary machinery of the age. The business was still small, but the ground was being prepared for a larger breakthrough. The breakthrough came from bevel gears. Straight gears were manageable. Gears that had to turn power around a corner were not. They were noisy, difficult to produce accurately, and prone to failure. In 1874, Gleason solved the problem with the first commercially successful bevel gear planer, a machine that used its own geometry to generate accurate tapered teeth. A part that had once demanded a master machinist could now be made repeatedly by an ordinary operator. That single idea changed the company's future. The original machine survived into the Henry Ford Museum as a founding artifact of American manufacturing. Its first customers were farm machinery makers and mill owners, but the company soon found a bigger wave in the bicycle craze of the late 1890s. Chainless bicycles needed small, precise bevel gears, and orders poured into Rochester. The craze faded, yet the lesson stayed. If you can make a gear that turns a corner, there will always be another place to use it. Gleason did not rely on bought-in parts. It built its own foundry and tool company so the whole process could be controlled internally, from molten metal to final machining. Castings were poured in-house, allowed to age so stresses could relax, then machined and hand-scraped to very fine tolerances. That vertical integration became one of the company's biggest strengths and helped turn a local shop into the Gleason Works. The business nearly failed after typhoid killed William's son, Tom, in 1877. 11-year-old Kate Gleason took over the books. She taught herself engineering from library books, became the first woman in Cornell's mechanical arts program, and then returned to the company as secretary-treasurer and chief salesperson. In the 1890s, she sold Gleason machines across the United States and in Europe, opening markets that made the Rochester firm internationally known. Her reputation became so large that Henry Ford publicly credited Kate with inventing the bevel gear planer. It was not true, but the legend spread anyway, and buyers sought out the famous Miss Gleason of Rochester. For years, she was the public face of the business, which makes her eventual removal from the company one of the harshest episodes in American industrial history. The automobile made the firm indispensable. Every car had to turn engine power inside the rear axle, so every car needed bevel gears. Gleason moved to a new University Avenue plant in 1905 and prepared for the coming boom. In 1913, James E. Gleason and engineer Arthur L. Stewart developed machinery for spiral bevel gears, whose curved teeth ran quieter and stronger than straight bevels. That innovation made the modern drivetrain possible. The new process led to a patent conflict with Packard, which held rights to the gear design while Gleason controlled the machines needed to make it. The dispute was serious because whoever owned the equipment effectively controlled the market. Eventually both sides settled. Packard kept the design rights and Gleason kept the machinery. Since every automaker needed the machinery, Gleason emerged with practical control over the equipment behind automotive rear axles. That same period broke the family apart. Kate fought for authority inside the business, lost, and was pushed out around 1913. She answered by building an even larger reputation. She became a court-appointed receiver, the first woman member of the ASME, a bank leader, and a developer of low-cost housing in East Rochester. After her death in 1933, history later honored her with the Kate Gleason College of Engineering. Kate's career after the split shows how much the company had underestimated her. In 1914, she was asked to rescue a bankrupt machine company in East Rochester and turned it around. In 1917, she took over the First National Bank of East Rochester and became the first woman to lead a national bank without family ties to the institution. She also turned to housing, drawing on the mass production logic she had seen at Ford. Her concrete homes in East Rochester were modest, durable, and meant for working families. She was not just a business figure or a novelty. She was a builder who kept finding institutions that others assumed only men could run. The company's technical line kept advancing after her departure. In the 1920s, Gleason engineers developed the hypoid gear. That mattered because it allowed the drive shaft to sit lower in the chassis, which lowered the floor and improved the car's center of gravity. By then, the company was not just making gears, it was shaping how cars were packaged. It also kept inventing specialized manufacturing processes with names that sounded like patents because they were. Each new process saved time, reduced noise, or sharpened accuracy, and each one tightened the company's hold on the gear business. William lived to see the beginning of that era. He died in 1922, and James E. Gleason took the presidency the same year. James held the role until 1947 and remained chairman until 1964. That meant one family's judgment guided the company through the age of early automobiles, the Depression, and the war years. Few industrial firms stayed under one bloodline for so long, while also staying at the center of a core technology. World War II was a proving ground for everything Gleason had built. Tanks, aircraft, and ships all depended on gears that had to survive enormous loads without failing. The company's machinery was producing components for Shermans, aircraft drive systems, and naval propulsion with tolerances measured in tiny fractions of an inch. It was the same principle William had learned in the 19th century, only now the stakes were national survival. After the war, the same precision carried into peacetime aviation and then space. Curvic couplings, with their exact face teeth and self-centering behavior, were used in jet engines and Apollo hardware. The company that had once solved the squeal of a rear axle was now supplying parts that could operate in aircraft and lunar programs. For a few decades after the war, Gleason sat near the top of American machine tool manufacturing. The Big Three bought its gear machines in huge quantities, and the company's name became shorthand for the product itself in the trade. A job there was often a lifetime job, and the apprenticeship system remained one of the most respected technical educations in the industry. It was the kind of place where fathers expected sons to follow them through the gate. Then the industry changed. Foreign competitors returned after the war with newer plants, lower prices, and stronger support. Detroit slowed, the American machine tool sector contracted, and Gleason faced losses, freezes, and layoffs in the 1980s. The company also had to deal with environmental cleanup in Rochester in the 1990s. Its answer was to keep innovating, starting with the computer-controlled Phoenix bevel gear generator and expanding into a broader strategy of total gear solutions. The 1980s and 1990s were hard for the whole American machine tool world. Japanese and European builders came back with modern factories and better financing, while American manufacturers were squeezed by recession and a strong dollar. Gleason still survived, but not comfortably. It froze pay, cut overtime, and let people go in a city already losing its industrial base. On top of that came state oversight of contamination in the Rochester plant, including industrial fluids that had built up over decades of production. The company did what it had always done in a crisis. It invested in a machine nobody else could match. The Phoenix machine was that answer. It replaced a forest of cams, cradles, and manual adjustments with computer control and servo motors. A setup that once depended on hours of wrench work could now be entered as numbers and repeated with far less variation. From there, Gleason moved into a broader total gear solutions strategy, buying companies and software so it could cover gear design, manufacturing, and inspection as one connected system. In 2000, the Gleason family took the company private again, choosing long-term engineering over quarterly stock pressure. That gave the firm room to invest, buy technology, and defend its patents in court. Taking the company private was not a cosmetic move. It was a rejection of short-term market pressure in favor of the long cycles machine tool companies actually live by. A gear machine might take years to design. years more to pay off, and then even longer to prove itself across an industry cycle. Public markets hate that kind of patience. Private ownership let Gleason spend on software, metrology, and acquisitions without having to explain every move to quarterly analysts. It also preserved the firm's appetite for litigation. Patent disputes against foreign competitors continued to be part of the company's strategy because the machine that can generate the gear is often more important than the gear design itself. Today, Gleason still operates from 1000 University Avenue in Rochester. Its modern machines cut and inspect gears under computer control, and its engineers are now tuning gear noise for electric vehicles. The company is no longer only a local manufacturer. It has operations and factories in Europe and Asia, and its modern systems combine cutting, inspection, and design in closed loops. Laser-based inspection can measure every part at production speed and feed corrections directly back into the machine tool. In the electric vehicle era, where there is no engine noise to hide imperfections, Gleason engineers are shaping gear surfaces to manage sound as carefully as strength. The question has not changed. How do you make power turn a corner without wasting it or making it a racket? The modern company also kept expanding by acquisition. It brought in firms covering cylindrical gear machines, metrology, and design software so it could offer more than a single product line. That mattered because the gear business had become too technical for any one machine to stand alone. Customers wanted the design tools, the cutter, the inspection system, and the service relationship to come from one vendor. Gleason's answer was to assemble that bundle piece by piece, widening the moat around its core business. The company's legal style never softened either. In earlier decades, it fought Packard over who could make the future of rear axles, and in later years, it fought foreign rivals in federal court over computer-controlled bevel gear generating technology. Those suits were expensive and slow, but they reflected a simple industrial truth. If you can prove your machine makes the best version of a critical part, you can shape the whole market around your process. Gleason has always preferred owning the process to merely selling the part. That attitude is part of why the company survived, while so many other American machine tool builders disappeared. It kept making the next generation of equipment before the old one had fully aged out. It kept investing when demand was weak. It kept training machinists and engineers even when the industry said the old shops were finished. And it kept doing all of that from the same Rochester address, which gives the story a kind of stubborn continuity that is rare in industrial history. The deeper lesson is that Gleason was never only about gears. It was about turning an abstract geometric problem into an industrial advantage, then into a business, and then into a multi-generational institution. William turned a famine immigrant's skills into a company. Kate turned crisis into reach, and later into a public reputation larger than the firm that dismissed her. James turned the company's inventions into the quiet drivetrains of the modern car. Later generations turned software, inspection, and global manufacturing into a new version of the same old idea. What makes that legacy durable is that precision is the product, not a bonus. In the industries Hardinge served, a tiny error could ruin a pacemaker part, an optical housing, or an aerospace component. That kept the company in a narrower but more demanding lane than mass-market machine tools, and it helped its machines outlast cheaper alternatives. Hardinge also understood that a machine tool is only as good as the ecosystem around it. Colettes, chucks, grinders, and service support all had to fit together, which is why later acquisitions mattered so much. The firm was not just buying revenue, it was building a complete precision workflow that customers could trust from setup to finish. The founders, the engineers, the wartime workers, the managers, and the machinists rebuilding old HLVHS all belong to the same chain. The company changed shape many times, but the standard never stopped being the point. That is why the company's story still matters. It is not just a story about one machine shop in Rochester, it is a story about how precision becomes power, how a family can build and lose and rebuild an industrial empire, and how one overlooked technical problem can shape everything from bicycles to tanks to electric cars. The factory still stands because the problem still exists. William Gleason crossed an ocean with nothing and solved a problem the industrial world had given up on. Kate Gleason saved the company, was pushed out, and built a legacy larger than the family that rejected her. James Gleason's machines made rear axles quiet, and the company that built them is still standing. One family, one factory, and one geometric problem: how to make power turn a corner.